For joining the first of hopefully many meetups, such meetups for the year 2022. My name is Nishith and I run Uber's data storage and compute platforms. That's one of the core components for all analytical data processing and management at Uber. A quick plug before we start, we're hiring across the board for all levels. So if you're interested in solving such challenges, please consider sending an email to the alias that will be shared later, or find me on LinkedIn. With that out of the way, we have some really exciting talks lined up for you guys today. If you have any questions for our presenters, please click on the Q&A box on the Zoom and type them out, and we'll try to answer most of them as they come along. So first, we have Surya and Meenal from Uber, who are going to talk about how we use Apache Hudi to perform large-scale data management and rewriting at Uber. So over to you, folks. Take it away.
Very warm welcome to everyone to the Apache Hudi meetup 2022. So we'll kick off the meetup with a session on the data rewriter platform at Uber using Hudi. So I'm Meenal Binwade, and I have with me my colleague Surya, and we are part of the Hudi storage engineering team here at Uber. So at Uber, Hudi powers a transactional data lake managing 200 plus petabytes of storage, spanning across 7,000 plus tables and dealing with 800 billion plus records each day. The Hudi consumes the change events from databases, Kafka streams, as well as incrementally from other Hudi tables, and ingests them into data sets which are stored on Hadoop compatible storage. These are then queried via the metastore by multiple query engines. Hudi also offers a set of table services. For example, the cleaner service, it cleans up the older snapshot files, freeing up storage space. The compaction service compacts the Delta files for an MOR table. The archiving service manages the Hudi timeline. Replication service replicates the data incrementally across data centers. And we have now also started using the clustering service. The goal of the clustering service is to rewrite the data to make it more optimal. So there are various requirements or many reasons why we may want to rewrite data. One of the important ones is to improve the data freshness. The ingestion pipelines provide a better write throughput when they write smaller files, but this impacts the file system performance, and it also impacts the query performance. So one approach to solving this problem is to let the ingestion pipelines write smaller files, but in the background, stitch them into larger files via clustering jobs, which will then improve the query performance. We've also seen significant query improvements when the data which is queried together is co-located. So if we sort the data on the columns which are part of the predicates, then this results in lesser amount of data that's fetched from the data, and hence it significantly improves the query performance. Other reasons could be for compliance purposes, such as encryption. Storage optimization could be another reason. Column pruning enables us to remove unused columns, freeing up unnecessary space. Also, file compression significantly reduces the storage space requirements. Prior to using Hudi clustering, data was being rewritten, but all of this logic was a custom logic outside of Hudi, and it involved either locking the ingestion pipeline or pausing it while the rewriting was in process. So some of the issues with this approach were that it did not update the Hudi metadata because it was outside of Hudi, and this resulted in data consistency issues. Also, this mechanism of rewriting is not compatible with the Hudi rollback and restore functionality, which is pretty useful when you want to recover from some consistency issues or corruptions. Also, the ingestion as well as the other table services cannot run concurrently with the data rewriting process, and thus impacting data freshness and SLA guarantees. So these were all the reasons we moved to using Hudi clustering as a default framework for rewriting data at Uber. Clustering provides pluggable strategies. It provides flexible policies, which enable users to select partitions that need to be rewritten. Different partitions can be rewritten differently. For example, for older partitions, we could delete unused columns. Also, for multiple partitions, we could sort them on different columns, thus improving query performance. Clustering also provides snapshot isolation and time travel. It's compatible with Hudi rollback and restore feature, and it also keeps the Hudi metadata in sync at all times. It leverages the multi-version concurrency control, enabling ingestion as well as other Hudi table services to run concurrently with the rewriting process. So with this, I hand over to Surya, who will walk us through the rewriter ETL framework.
Thank you, Minal. Yeah, let's look into the rewriter ETL framework with Hudi clustering. Yeah, so this is an internal framework created to run Hudi workloads, Hudi clustering workloads. It consists of mainly scheduling component that actually runs the clustering jobs. We generally define clustering contracts in the form of a configuration file, and this file is actually deployed using this framework. I will cover in detail about the configuration file in coming slides. And yeah, so this framework also supports different types of pipelines like incremental and backfill. So let us suppose today you are trying to deploy a contract, a clustering contract that says sort the table for me. And if you have started an incremental pipeline, it runs daily once, and which actually sorts a previous day's partition. But what happens to all the older partitions that are left out? For them, we create these backfill pipelines, which run in high parallelism to cover all the partitions. And just to explain the scale at which we can run clustering operations, at Uber, we ran close to 20 clustering jobs simultaneously clustering 20 partitions on a single table. So we are able to achieve this due to because like clustering supports MVCC, and also because of the various guards and checks that we have enforced in the framework. And obviously, monitoring and alerting plays a key role in finding out the faults and addressing them. And all these solutions come right out of the box for all the tables that are onboarded to clustering. Next slide, please. Yeah, so now let's look at an example, an incremental pipeline, where this pipeline is trying to sort a trips table. And as I said, like this pipeline runs once every day, sorting previous day's partition. And if you zoom into a particular execution unit, you will see 3 different tasks. The first task is the Hudi clustering task. This is the task that actually does the clustering operation. And after which you have a failure detection task. So what this task does is, if there are any failures that are found in the previous stage, it tries to roll back the in-flight files. That way it can keep the commit timeline clean. And finally, we have a post-process validation task. In this, basically what we are trying to do is make sure that reader side there are no issues that are encountered by just querying Hive or Presto, by just querying Hive or Presto queries. We are trying to see the partitions that are currently like that are clustered are actually working fine. Next slide, please. Yeah, if you deep dive into the clustering task, we have a first step was a rollback task. So the failures in clustering operations are quite common because of a wide variety of reasons. And so we have incorporated a retrail logic within the clustering task itself, which we'll try to reiterate twice. And to clean out the previous failed runs, we use this rollback task. And after which we schedule and execute clustering. And after rewriting the data before committing the files, we basically do some pre-commit validation, where we run row count and checksum queries on the previous and after state of the data. And once all this are successful, then that's when we do a replace commit on the timeline. Next slide, please. Yeah, so this is the YAML configuration file I was talking about. So clustering contract is actually defined using this file. And here we give bare minimum configurations like, what's the Hive table used, what's the scheduling interval looks like, and execution engine, etc. We also have something called an action type called sorting. So this is nothing but the different use cases of clustering. You can have anything like sorting, stitching, column pruning, etc. here. And we also use for any reason, if you want to pass some custom write configs, you can also pass them through this configuration file. Yeah. Next slide, please. Yeah. So the rewriter ETL basically takes this YAML configuration file and creates a config object out of it. And all the pre-commit validation queries that we use, those queries are actually generated right here at the generator, and then gets appended to the config object. And the framework actually translates this into a Spark runtime arguments and starts the clustering job. Yeah. So let's look into the challenges and lessons learned. Backfill versus incremental. So running backfill pipelines with high parallelism, we have noticed some bottlenecks around archival job. So we did some optimizations to fix that. And resource management, as clustering requires more resources than an ingestion jobs. We need to fine tune the jobs and come up with rough estimates on the resources before actually onboarding the tables. So we do some test runs on copy of the production tables and then come up with these values. Alerts and metrics. So you can see like different types of failures while running clustering jobs, especially for backfill. There can be like resource utilization issues or any dormant issues in the partitions, or if there is a ingestion job is trying to update the same partition. Since we give priority to the clustering job, we try to fail the clustering job there. So all these kinds of issues, all these kinds of failures can result in a lot of alerts. So we also have a retrail logic within the clustering. So we do not want to raise a lot of noise while alerting for non-retriable errors. So we have to make sure we alert properly. And onboarding thousands of tables. As I mentioned, like each clustering contract is actually configured using a YAML file. Like onboarding thousands of tables would involve creating thousands of YAML files. So this is a lot of wastage for developer time. So, and also the multi-writer. So we have seen like multi-writer is already solving a lot of race conditions while running clustering in async. So we are actively testing this out to release these changes. Ongoing and future work. So yeah, so we have a lot of work that is we are currently doing on clustering. Couple of things that we want to highlight are one is the centralized config store. We want to use the same Hudi write configs across multiple writers like ingestion, clustering, etc. And also we also trying to build a tool to automate the resource estimation. That way the onboarding process is much more streamlined. Yeah, finally, we are hiring. I think it's an exciting time to be part of Uber and also data lake space. Yeah, please reach out to us within the mail given there. And yeah, thank you. And any questions?
Thank you, Surya and Meenal. Folks, if you have any question, please type them out in the Q&A box. Even if you have questions later for the previous presenters, we can answer them on text. But thanks Surya and Meenal for the sharing your insights on how clustering can be used scalably. So next up, we have Vinay, who is going to talk to us about how they use Hudi to manage CDC on their data lake in Disney. So Vinay, over to you.
Yep. All right. Hey, hi guys, everyone. Excited to be a part of this meetup. So today we are going to talk about how we migrated our CDC data to Hudi. Quickly talking about myself, I'm Vinay Patil working with Hotstar and a data platform team over here where we manage the entire data right from ingestion layer till the time data is stored into our data lake. A quick overview about Disney Plus Hotstar is the #1 OTT platform in India with over 500 million plus downloads. We achieved a peak concurrency of around 25 million users where, let's say, just like baseball is in the States where it is widely followed, it's similar in India, cricket is followed over here. So that's the peak concurrency that we had followed during the World Cup. Hotstar is available in more than 15 plus languages. We have a variety of content, be it live, sports. Also, we have a regional catalog that's available in more than 15 languages. A quick overview of scale at Hotstar. When I'm saying Hotstar, it's Disney Plus Hotstar over here. So a quick ingestion patterns, as I mentioned, about 25 million concurrent users that are watching a particular match. Now all these events are getting fired to Kafka. So roughly we have 1 million events that are ingested per second. The projection is around 50 billion events per day. Storage patterns is roughly 14 TB data per day that is stored across S3 and HDFS. Our consuming layer is basically via Hive, Presto, Spark, streaming jobs that are basically querying live data from Kafka. So I'll walk you through the current agenda and what you can take away from this talk. So basically, we'll start with how did we process CDC stream before Hudi? What were the limitations of that particular flow? Then we'll talk about how did we make use of Hudi for our CDC flow. We'll walk you through the POC phase, what were the initial findings from the POC, how we productionize our jobs to migrate 200 plus tables containing terabytes of data to Hudi. What were the challenges? How did we choose between the different table types and future work that we want to try out with Hudi? So the older flow that we had was using HBase. So just to set some context, we had 3 different sources of data, change data that was coming into Kafka. We had Dynamo streams that were enabled on top of DynamoDB. We had Debezium source, and we had a custom format. It could be S3, it could be from ES, where team used to just send the change data to Kafka. Once the data was landed to Kafka, we had a Spark streaming job, which would pull in this data, do some transformation on top of it, write this data to HBase. The reason we choose HBase was one, you get out of the box absurd support with HBase. It's a key value store. Now, once this data is stored into HBase, we wanted this data to be present into your data lake, S3 for us. So what we did was we scheduled periodic snapshots in Airflow roughly at interval of about 3 to 4 hours. Now, what that snapshot job does is it does take the entire dump from your HBase table. It does a select star from, hey, HBase table that is backed by Hive, basically, and insert into another Hive table. You see the problem over here, right? You're actually doing a dump every 4 hours. And some of these tables are actually big tables containing billions of rows. Just to talk in terms of numbers of HBase, we had roughly around 100 million requests that are coming per day. You also have read requests parallelly on HBase, which is roughly around 500 million. These are streaming jobs that are relying heavily on HBase for doing enrichment. We have snapshot jobs that are actually scanning this data, let's say after every few hours. And this consumption pattern is not on the HBase per se. Like HBase is only for the scanning purposes. That's why what we did was we did not expose the HBase to end users. It was only a platform and the snapshot jobs which was actually scanning this data. If we had exposed the HBase to the end users, it would have impacted badly on HBase performance. So we'll talk about what were the limitations of this particular approach. The first thing is, as you can see, we have duplicate data that is residing into HBase and S3, which is highly cost inefficient. There are too many touch points in the approach that we have, wherein one, you have to spin up, create your HBase tables, you have to create HBase Hive tables, you have to schedule the Airflow snapshot jobs, you have to create a copy of your Hive tables. Now, these are too many touch points, and that gets tedious whenever you're onboarding a new data source. The important part is you end up having a very large latency. Since you're spinning the snapshot jobs after every 4 hours, and some of the big tables usually take more 4 hours to complete. So you are roughly talking about 7 to 8 hours of delay just to get the data for doing any kind of analysis. Now, this gets hard during, let's say, a very important match like India versus Pakistan. Let's say if I want to do some analysis on top of the CDC stream data that is coming in, I cannot do that today. And hourly snapshotting was just inefficient. We couldn't just enable hourly snapshots and take the snapshot, right? Because it would lead up to HBase issues. And we had seen that in the past, where, let's say, if you do frequent snapshotting, it would lead to HBase issues in terms of, let's say, CPU IO weight going high on one of the region servers, and it directly impacted your other streaming jobs that are important for us. So it was actually after, let's say, onboarding multiple geos, we thought of that, hey, this is not scaling up. We need to find a new solution, a better way of dealing with this. So we started exploring the frameworks out there, Delta Lake, Hudi, and we started with Hudi. So with the Hudi flow, what we wanted to tackle is we want to remove this 3 red boxes that you see. We want to get rid of HBase. We want to get rid of those snapshots. So it would just be the same pipeline. It would just be Spark streaming plus Hudi. You still have those S3 backed Hive tables, but now this is the Hudi data that is coming in. We started with the POC phase with the expectations that, hey, there are 3 important expectations from this POC. We want to ensure that the data is correctly getting updated for a key, right? Because that's what was happening in HBase. Your query returns the latest updated record always. Deletion of the key is possible for GDPR purposes. It could be soft or hard delete. So we started out locally with a Hudi Docker setup just to get familiar with Hudi concepts. I would highly recommend to start with this particular approach. Next on, we evaluated Hudi on EMR with a small use case just to get hold of what are the things that we could utilize for migrating our data with big tables and productionizing it. So we started looking at Hudi Delta Streamer for processing JSON as well as Avro data. Figured out, okay, you have 2 different types of tables over here: copy on write, merge on read. Looked at compaction, clustering, config. This was on a very high level that we were looking at. Hive sync is a big win on EMR. You basically, the tables get created on the fly for you. We also worked with Hudi CLI to figure out the options that are provided in the CLI configurations. It provides you a bunch of options for seeing your commits, compaction. So do check it out. Once we after ending this POC phase, we had some initial findings. So the expectations that we had from this POC that were checked. So the data was getting correctly updated for a particular key, or the query always returned the latest record. Deletion of the key was possible, and the bonus was the Hudi takes care of small file problem. So that was a bonus for us because we have a different pipeline which takes care of doing this. So this was a bonus for us. Now there were a few items that were not working for us when we tried this out on our own cluster and not on EMR. So first was the Hudi data streamer did not commit back the offsets to Kafka. Now why this was important for us? Because we heavily rely on consumer lag alerts just to be sure that we are not, let's say during the match, if there is a high lag, we want to make sure that we are scaled up or take some action on top of it. So we basically worked upon it, contributed back to the community. Now with the newer versions, you can actually commit the offset back to Kafka, read from a committed offset as well. Do check those configurations out. It's already live. Hudi CLI did not work with S3 for us on a standalone cluster. We have OpenPR out, which we have tested in Hadoop 2 and Hadoop 3 environment. The Hive sync as well did not work with S3 on a standalone cluster for us. There are some discussions on the issue that I have linked over here. Now, with those initial findings, we started productionizing our jobs. We wanted to migrate, as I said, 200 plus tables to Hudi. So the first important thing was we wanted to automate our backfill jobs. And Hudi, it does provide you the option to backfill data for the Parquet tables, but all our backfill data was in ORC format. So we automated this backfill jobs to migrate these tables. One suggestion over here is make sure you're using bulk insert mode if you have the data in, let's say, if you don't have any duplicates in your end data set, make sure to use bulk insert mode. The backfill runs faster. Now, we also automated the Hudi table creation flows just because our Hive sync was not working. So whenever you want to, let's say, onboard a new table, it could take care of table creation for you. So we started with migrating big tables, which were consisting of 4 billion plus rows. We had to do some kind of tuning to handle these small file issues. Initially, when we started deploying the job, we observed that with the default configuration that we have set, we got around 30K small files. Now, that's a huge number in terms of, let's say, if you query those data set, the runtime is high because of the small file issue. So we started tuning one of the configs based on discussion with community. So we upgrade this config to 6 GB, wherein we got roughly around 669 files, which were okay for us because it was creating around 1 GB file. That was a good enough number that we stayed at with for all the jobs. There's a Jira ticket as well. I forgot to link it over here. There's a Jira ticket for it as well, wherein we talked about the issues faced and it faced over here. All right, how do we choose between copy on write or merge or read table? So we initially thought of, hey, why not just use copy on write table for all the use cases? So we started deploying the big tables with copy on write configuration, and we observed that it took around 30 to 40 minutes for each batch. The downside was the lag started increasing for us. So we went ahead and started checking out for smaller tables with copy on write, and then we get to a conclusion that okay, for smaller tables which are having less frequent updates, or the SLA is pretty much within our time, right? So we took the option of deploying copy on write only for smaller tables with footprint of, let's say, 500 million or less. We reduced our SLA from 4+ hours, as discussed. The snapshot went away, right, from 4+ hours to 10 minutes over here. That is a big win for us. For bigger tables, we are using merge on read table type. The SLA for such tables has reduced from 8+ hours to 1 hour. That is after compaction. You can basically read a query from the merge on read table type as well, wherein the SLA is even lesser. What were the challenges that we faced during this productionizing our jobs? There is also a JSON source, as I talked about, Dynamo streams, right? That is a JSON data that is coming in. So we observed that we faced some schema evaluation issues in Hudi 0.8 version. So let's take an example. On the left side, as you see, you have only two fields over here. You have first name and country. Now, let's say in this next batch, you get first name, country, and last name. It used to throw this particular error that Parquet or Avro schema mismatch, the Avro field last name not found. This is when we started checking this out. This is more of a Parquet issue than the Hudi issue, and Parquet also says that this is expected if you have such schema mismatch at the source itself. So what we tried to mitigate this, we created a Uber schema in SR. When I talk about Uber schema, that means you will have all these 3 columns in your schema registry, and you will use that schema while writing the record to your DFS. That means to writing to Hudi. The disadvantage of this approach is whenever new field is added at the source, we have to update the Uber schema. But you take a hit on it rather than failing the job right now. With Hudi, the newer versions with 0.10, you have an option to reconcile the schema as well. That should actually solve this particular issue. Learnings from this process. Let's say these are also key takeaways from you whenever you want to migrate your jobs to Hudi. Make sure that the migration process is black box for the end users, so that your end users do not know that, hey, underlying you have a Hudi format that is coming in, and there are no changes that your end users have to do. That's what we tried doing it over here. We already had views on top of our Hive tables. Now the views are pointing to your Hudi Hive tables. So no change on your ETL side, no change for the end users who are querying the data. For Spark users who are deploying the jobs on our platform, we copied the Hudi bundle in Spark JAWS folder, so that you do not have to explicitly add the Hudi bundle and packages. That would work out of the box for the Spark users as well. Another key point is choose your compaction strategy correctly for the merge on read table type. This is because one thing we observed that this is a recent thing that we observed, wherein for a streaming job, it was continuously doing the compaction because our batch time was higher. So that's why with the default configuration, every batch was actually doing the compaction, which lead to increase in lag. So what we have done now is we have set the compaction strategy to number of commits and time as well. So that gives us a breathing room of when the compaction will trigger. Choose your cleaner configs correctly to avoid any ETL failures that are dependent on it. The next one is we had to upgrade to Hudi 0.10 for a merge on read table type because of a recent issue we faced with data quality issues we faced, where intermittently we were getting lesser row counts when we were querying the data. Let's say our ETL ran, let's say at around 5:30 a.m. So it was reading lesser rows and alerting us. So when we retried those ETLs again, it used to work. But upgrading this to a Hudi 0.10 has solved that for us. There are a bunch of changes that went in with 0.9 and 0.10 for merge on rate table type. Do check those out. The last one is important. Keep your older flow running for some times. This is to make sure that in case of any issues, you can rely on that flow for doing the backfills. We have faced these issues. It could be anything. It could be your code that you have written for the Hudi migration, or it could be any other issue that you will face. So keep that older flow running for some time. Get some confidence from your analytics team that the data that you have written with Hudi is correct. And if not, you can always rely on that older flow for doing the backfills and correct your code or do some corrections. All right, the future work that we want to do with Hudi, we are already planning this out. So faster analytics using Hudi take advantage of those of the merge on rate table type to get faster insights. Just like I talked about, like let's say during an important match like India versus Pakistan, if I want to get faster insight, I should be able to do that. And today I'm able to do that with the CDC flow. I want to enable it for other sources as well. Built-in data lake in near real time using Hudi. We plan to migrate petabytes of data to the Hudi flow. Contributing back to the community, we have a couple of issues. Dynamo streams source we want to enable. As we're already using, we want to work on that. Choosing between Flink or Spark with Hudi. Currently, you have Hudi Delta Streamer. You also have Hudi Flink Streamer as well that you can use. So with this configs, you would be able to choose between Flink or Spark. Good, that's it from my side. I'll take some questions if you have any. Thank you.
Thanks, Vinay, for such a detailed presentation and sharing your learnings, how you productionize these tables. I think there are a few questions. Do you want me to read it out? I can read them out actually. Maybe
yeah, sure.
Answer them. We have a few minutes. Yeah. So from Kyle, can you share more about your use case of Delta Streamer committing back the offsets to Kafka? What do you do with these offsets? Some multi-read write kind of?
So yeah, Kyle, this is basically for monitoring purposes for us. So when you commit back, you can monitor your job, like with how much lag it is happening. So that was the main purpose of doing this.
Got it. The next question from Istwan, hope I'm pronouncing it correctly. So in-place upgrade is not possible. Let's say changing from v0.8 to 0.9 to 10 and so on over the same data backend.
In-place upgrade, I did not get that. Do you mean to say when I upgrade from 0.8 to 0.9, upgrade the version, will it not work?
I think that's the question, that whether
I think
yeah.
So for us, it did work. Like we went from 0.8 to 0.10 for one of the job just by changing it in the packages, and it worked for us. So it should work out of the box. There shouldn't be any issues.
Sounds good. Yeah, I think that was his. Then the next question is, thanks for the great presentation, Vinay, from Nodir. My question is, how do you manage real-time Kafka ingestion and deletions from, for example, GDPR simultaneously?
Yeah, that's a good question. So we basically do not do it simultaneously, the GDPR deletions. Let's say if you want to do a hard delete, right? You have a different flow. We have a different flow wherein we take some time to delete that data. We tell the user, hey, data will be deleted after X number of days. So you take some time. You do not do hard deletion immediately. I hope that answers your question.
Got it. We have time for one more. Last question is, this is some very impressive engineering work. How long did it take your data lake project from start to finish? What took most of the time?
Thank you for asking that. So it took us roughly around 5 to 6 months to productionize everything. Mostly the time it take was in our POC phase, as I talked about. So the time went in there. Also, we wanted to try out with Delta Streamer. Then we went back and forth of whether to choose Delta Streamer or get started with the Spark streaming that we already have. And then we went ahead with, hey, let's reuse the stuff that we have already built, add some transformers over there, and get started. So yeah, it's 5 to 6 months where we're in doing the POC and productionizing it. So mostly we have all the stuff in production right now.
Got it. Thank you. I think there's one more question, Vinay. Maybe if you can type out the answer, since we need to get over to the next.
Yeah, sure. Thank you.
Thank you. Awesome. So next up we have Sam and Troy. They are going to present about how Hudi is powering their data lake at Walmart. So over to you, folk.
Thank you very much, Nishin. So I'm going to be talking a little bit about our journey towards what we're calling the modern data lake or Delta Lake. Excuse me. I'll share my screen and presentation. Give me 1 second. So I'm Sam. Troy and I both came from Jet.com. I was part of Jet's product team leading data product at Jet. Now within Walmart, we're both within platforms. I manage 3 teams within stream processing domain, and Troy is a distinguished engineer within the Walmart space within data in motion, which is messaging, telemetry, and stream and batch processing. So what I want to kind of talk about is our journey towards how we ended up where we're at today in this kind of new modern architecture. And I'm going to start with kind of the legacy architecture. What were the pain points and how did this kind of evolve into what we have today? And so this is kind of a stack of what it looked like at Jet.com, which was obviously an e-commerce site with a bunch of different microservices running in the background, keeping that site running. So rather than specifics around like order processing, basket management, website, inventory, and things like that, I'm just going to call them domains. Hopefully this type of architecture resonates with some of the people on the call. So we were an event sourcing company. And so basically we managed and wrote immutable events within data stores. And so every domain as a microservice, for example, we'll go back to the e-commerce example, and we'll talk about like an order management system. You would basically project an immutable set of events of everything that happened into what we used was event store, but it could be any other type document store. And since those events were immutable and they were indexed really fast against a partition key, but not so accessible for other types of access patterns, most of these teams ended up reprojecting their same data to like SQL servers so that they were able to provide more advanced use cases on their platform that couldn't just be resolved by a single entity or a single set of events. And so as we saw this platform evolve and grow more and more complex, everybody needed a shared bus. And so we, of course, selected Kafka, like a lot of companies, to share events between different domains for asynchronous processing. And what ends up happening is it ends up being very bidirectional. So teams obviously are consuming data from other systems. So order of data is flowing to marketing teams, it's flowing to the website teams, it's flowing to search teams who all use that data for different business use cases. And what you end up with is obviously reproduction or duplication of data across all these different domains. And there was no standardization. The only place that data sort of eventually resides was in our like tier 2 and tier 3 analytics layer. And so a lot of teams that obviously segregate production data needs from analytical data needs, there's typically a hard line in the sand that those two don't mix. And so what we ended up with is for the production SQL servers, we would use always on replication and move OLTP workloads back to OLAP workloads and expose those to analysts and data scientists. But we also obviously, like a lot of modern teams, we're building a data lake and a data warehouse. So we would ingest the raw data using a technology like Flume, push those raw events into cloud data stores like GCS, S3, and S3, GCS, and Azure Blob Storage. And then we would take those raw events and use batch processing pipelines to then schematize that data, clean it and repartition it and dedupe it and put that in our data warehouse. And so a lot of this custom application code was built to just basically surface this data. And much like a lot of the other presenters, we use Presto as an acceleration layer, Spark for kind of ML, AI, and more advanced use cases, Hive workloads and the Hive Metasort to register those tables, and a bunch of BI tools that sit on top of this. And so like this was a pretty good stack, and it got us through a lot of our needs. We stored many petabytes of data and we solved many use cases with this. But what ends up happening is a lot of these production teams who needed that data wanted a lot of the derived data sets that were being generated in the analytical layer, and there was no way to bring those back with desirable SLAs. So some of the pain points in here is obviously you have loosely coupled systems here that are using like JSON or other messaging layers to communicate, and so schemas would break quite frequently. Data between the systems would obviously grow stale. You'd have duplication of data across domains, and you have many, many issues. Obviously, you see many, many ways of getting data between systems. So you have complex data paths. And we also have this like strong desire to bring data back to production that's in the analytical layer. And that's very complex in the system because things could break, and bringing the data back to a production system in this fashion wouldn't work. So what was the first step towards where we're at today? Was basically generating a stream processing framework for production and hosting like a production data layer that sat outside of the analytical data layer. And so what we started to see here is we wanted to reduce some of those pain points. You'll see like we start removing these kind of like domain specific OLTP systems in favor of something that scales really large like Cassandra, and we expose it via an API back to these application teams. And so we wanted to express that as a standard framework for all teams. And so the next slide, I'll kind of show you what that framework and how that framework evolved into what we're doing with Hudi. But we have a bunch of events going into Kafka. We have a set of jobs that we called projectors, which were kind of mapping that data into a heavily schematized form, loading it into Cassandra and exposing it back to application teams via an API. And we didn't want to build a production monolith. So one of the, I think, key findings here was not just one massive cluster for all of our company, because we were processing millions of events per day, billions probably. We decided to make that a set of Cassandra clusters abstracted through an API and a data model. So like this isn't one gigantic monolith, but rather a bunch of these that are all managed by one team. Secondly, we started finding that we needed to aggregate the data in real time. So we kind of abstracted that into what we called listeners. You could think of those as mappers and reducers. And so for every projector, we wrote to Cassandra, emitted change stream messages, and either further derivation of data could be used via listeners, which could reference external state stores like Cassandra, pull data back in and aggregate it and push it back in real time. And ad nauseum, we could build like 10-layer deep pipelines, aggregating real data, data in near real time to Cassandra. But we need that data in analytics layers as well, right? And so the first thing you start saying when you start exposing this, and is very much the same thing that Vinay was presenting, is that you want to get this data out of Cassandra or HBase, and you want to start putting it in your data warehouse. Or teams basically say, hey, we have these batch workloads and we need to start running things that you can't look up against the point lookup like Cassandra does very well. So I need to do a full table scan, which is an anti-pattern for Cassandra. So what do you start doing? You start running Spark batch jobs. You start extracting that data as frequently as you can. Your collections continue to grow. That puts pressure on Cassandra, puts it in a bad state, slows down ingestion, and everybody gets very angry about this. So we've done some improvements with what you see here, but we still kind of have this like two-tiered solution where we're like doing an anti-pattern for Cassandra and pulling a lot of data from it. And secondly, what you also see is we still have a lot of complex data paths here. So things are like running all over the place, but we have reduced some of the complexity and data duplication in this. We still obviously, like I said, have some pain points we'd want to resolve. So just a very short peek without looking at actual code of what that stream processing framework was an abstraction using Scala on top of Spark. We abstracted what we call the model, which was kind of like the end state schema of what we expected. We reuse this for how we store the data in our Hudi tables as well. We have the projector code, which could be expressed either as Scala transformations or Spark SQL. So we'd register a data frame and then schematize and transform the data to that final model. We would build integration tests. So as you're building out these things, you could make assertions on sample jobs and basically do all your local dev environment and have confidence in your pipelines before you deploy them. And we'd have standard CI/CD to get those applications up and running. So kind of as an objective to be able to produce hundreds, if not thousands of these pipelines, the goal was to be able to build a pipeline in under an hour. So the idea is very self-service, exposes to all the different application and domain teams and get them to centralize their data and then expose it to analytics for reporting, but also have like a production source of truth for that data that teams could leverage. And so then where does that get us to today, and where are we still moving towards? So obviously over time, Jet.com merged into Walmart, and a lot of these platform tools have become part of Walmart tooling. And so we have some use cases. And so we investigated Hudi quite early on, and we started looking at it because back in the early days, we built our own custom framework for deduping and merging data into HDFS. It's not very sustainable to build your own. I think the Hudi framework provides a lot of the semantics that we would need, if not all of them. And so where we're at today, and I think some of the nice architecture that you'd want to see is similar to what you had before, but we've built archiving services, which take the raw events and push them down into HDFS. These archiving services ideally just point to a Kafka topic, partitioned by event time, and put the data in automatically. You can instantiate them automatically through a GUI, or just basically through some CI/CD flow, or automated directly with Kafka itself. Secondarily, we would have data projectors, which reuses that framework we used before, but obviously has some additional semantics around partitioning of your data, row keys and versioning, and how you'd want to version your data. And then maintain duplicate projections, both to your data store in Cassandra, and then also into your warehouse or your lakehouse. Lastly, we still want to maintain the listener framework because it enables you to do near real-time projections of data. So I think what you have here is a far cleaner approach to getting production copies of data, both in a point lookup system as well as an analytical system, where you can maintain relatively low latencies between them without all of the complexities that you saw before. It simplifies the data paths dramatically, reduces duplication of state across all the domains. We've solved most of the issues, I think, here. And so we want to scale this, I think, across Walmart's gigantic data lake that we have today, which is primarily Parquet files and ORC files. And this also reduces a lot of teams' desires to do batch reads against Cassandra, because you have a pretty low latency copy that you can work with rather than a 24-hour latent copy that teams kind of snapshot and dump tables today. So with that, I would kind of just want to talk about one production use case in general, but obviously this is repeated across many production Hudi pipelines that we're running today. So what we have today, for example, is an existing customer with a very large Cassandra collection, something on the order of 25 terabytes, 500 million large records sitting in production. It's a source of truth. Obviously, it's being written to perpetually. It's a very write-heavy workload. Sorry, it's a write-heavy workload with reads for tooling and other point lookup systems, but it's the production source of truth for many of these teams. We're a very heavy Cassandra shop. And so this 25 terabyte collection today has many, many consumers of data that are being exposed to that data set, doing batch reads against it, pulling data from it. And as this has grown from a very small collection, maybe 50 to 80 million records to 500 millions to hundreds of terabytes of data in some future state, it becomes a very difficult task to pull the data back out. So let's just look at how the data gets in there. So it's coming from 2 of our data centers. And so basically that data is a very heavy payload. It's somewhere between 100 kilobytes to 1 megabyte in Kafka. And those records basically need to be persisted. It's running hot in 2 data centers. So updates are basically need to be inserted idempotently. Cassandra solves for that with version keys really well. Secondly, it's 100 to 500 events per second across the entire day. We're merging about 330 gigs of data into our final table. Cardinality is slow growing. So what that means in this case is we're doing very frequent updates to records and very slow growth or inserts. Secondly, like I said, it's running hot, and so we want duplicate writers writing data, and we need idempotency because we can't guarantee order of events, and we also can't guarantee delivery guarantees. We're doing at least once guarantees in almost all of our systems. And so we'll talk about the other challenges and why Hudi solves for them, but I think ideally you're looking at the same framework we're talking about before, pushing data into Cassandra, emitting change streams back into Kafka, processing those and archiving those for backfill and replay purposes, as well as loading the data back into what we're calling our Delta Lake. So with this, the latency of ingestion can be down into minutes using merge on read tables. Cassandra can keep the point lookup copy of that, and teams are now able to point their batch workloads to this version, and which frees up a lot of the Cassandra cluster and allows us to reduce the scale and size of that over time as this collection continues to grow. And then, okay, so what is it that enables this for us, and why do we really like the Hudi features that have unlocked this and other use cases? We like the optimistic concurrency or MVCC controls that are available to us. We've done a lot of work around asynchronous compaction. Most of our production workloads today, I think much like Vinay had hinted at, we're using inline compaction after so many batches. but most of our Spark workloads are over provisioned because of that, because the compaction takes far more resources and time than ingestion. So we're in the process of looking at doing asynchronous compaction rather than inline compaction on our merge on read tables. We also want to reduce latency, and so we leverage merge on read tables significantly because that enables us to append to data much faster. We also love native support for deletion. It's something we had custom frameworks built for things like CCPA and GDPR, where somebody would put in a service desk ticket and we'd have to build an automation flow to remove records from HDFS. This comes out of the box for us. Row versioning is really critical. Obviously, a lot of our pipelines have out of order data, and we need the latest records to show up. And so we provide version keys for as part of our framework for all upserts into the Hudi tables. We also like the ability, although we don't have a lot of users yet that are using incremental and snapshot queries over historic snapshots. But the fact that customers can pick and choose how many versions of a row to keep, be able to provide snapshot queries and get incremental updates, like what's been updated in the last 5 hours, is really powerful for a lot of users. Things that we're evaluating, and I think things that we want to be able to do with the framework. One is bundle the jobs, right? Like obviously operational maintenance of numerous jobs can be really difficult. So we want to be able to bundle those jobs into something that's easy to manage and easy to operationally leverage over time, because what we do for one pipeline, we're going to repeat thousands of times to basically represent our entire data lake ecosystem over time. We also want tight coupling with our internal systems. We have data quality systems, telemetry systems, reconciliation systems, and the schema registry. So I think it would be great if these Hudi libraries and everything we expose to our end consumers are tightly coupled with that. We also are a heavy Kafka Connect, and we're on the edge of offering Flink internally. So I think we need to understand how those runners also work with the system and find the best in breed technology that we'd like to use. Again, I think we have more work to do on investigating background compaction and specifically clustering. I think a lot of these tables that are in Cassandra are partitioned a specific way intentionally. Reclustering our data as data comes in is really valuable in terms of query performance. So I think having background compaction and clustering is critical versus trying to do that inline. And the last thing is we need to invest a lot more heavily in terms of production tooling and automation. You know, our scale is quite small right now in terms of deployments, but over time, without that, I don't think we'll be able to scale. And with that, I just wanted to say thanks for the opportunity to present what we're doing within our ecosystem and open it up for any questions anybody has.
Awesome, thanks, Sam. That was extremely detailed, and I got to learn a lot about changes and how things are being absorbed. Let's see, do we have any questions? I don't see any questions as of now. Folk, if you have any questions for Sam, please type them out in the Q&A box. Yeah, I think that's our last talk for today. So we can wait for a couple of minutes and see if people have questions. And then if not, then we can end the session. Oh, I see a few questions pop up. I can read them out, Sam, if you like, and maybe you can answer them.
Sure, yeah, absolutely.
So from Vishnu, how did you handle the transition to Hudi from legacy system?
Yeah, I think basically where we've been at is it's very iterative. We're not going to do a lift and shift of everything. So it's kind of 1 or 2 pipelines, 1 or 2 customers at a time. The idea is to build a self-service framework. And I think a lot of the initial effort around data validation and bootstrapping data is where we're spending most of our time. So I think the honest answer is it's still a journey for us, and we're spending a lot of effort and time in trying to how to automate that more. But it's 1 pipeline, 1 data set at a time right now for us.
Got it. Another question from Sean. Why did you pick Hudi as opposed to other technologies like Iceberg, Delta Lake? Yeah.
We started quite early in our journey. So I think we picked Hudi over, and at that point we were running our own internal framework, basically to mimic some of the same functionality of Hudi. I think when Hudi was really early on, it was probably a little too early for us, but it was the one we did the investigatory work first. We also wanted to tie ourselves to open source framework. So we did stay away from Delta at that time. And then I think in terms of Iceberg, it just wasn't it wasn't mature as Hudi at that time. So I think we made a decision and a distinction for Hudi quite early on. We've since been reinvestigating and reevaluating all the technologies because they're all evolving. And so Iceberg and Delta are still on our roadmap, and we're still evaluating them right now. Just in terms of Walmart being so large, we have many use cases.
Got it. Question from Craig. Any notes to high level share in terms of getting Hudi stood up in Azure, or was that straightforward?
It's as straightforward as anywhere. I think, I don't know your Spark runtime, but we didn't have much difficulties. I think the biggest difficulty early on for us was Azure Data Lake versus Azure Blob Store. WASB containers were much slower for these workloads because file movements are not metadata operations. Once we went to ADLS v2, I think everything was much faster, but trying to run these workloads in WASB, you would see a drastic performance difference over like GCS or S3 or wherever else you're trying to run it. So I think as long as you're using ADLS v2, I think you'll see good performance. We still do see some throttling on containers for our very heavy workloads. So I would say you have to be very, I guess, careful with how many different workloads you put per container. So just keep an eye on like throttling, but otherwise there's been no issues. It's very easy to get it up and running.
Great. Another question from Nadir for both Sam and Vinay as well. Follow-up question on deletion. Do you need to turn off ingestions to perform deletions? Excuse me.
Yeah, it's really early days for us as well with regards to deletion. Most of the data sets that we've onboarded don't require that. We do have a couple teams that are under kind of CCPA compliant workloads and do need that. So that's very early days for us. I don't know if Vinay has a stronger answer for how he does it, whether they pause ingestion or they do that asynchronously.
No, we don't pause our ingestion. So as I said, it's a different job altogether that takes care of deleting the data.
Okay, great. Another question from Sean. Are you/Walmart also contributing to Apache Hudi development?
Yeah, we've been open. There's been a couple like defects and bugs, and I think we've been working with the team to like fix what we saw in the early days. Since then, yes, as features come up and as we're involved in the ecosystem, we want to contribute back, absolutely. Yeah, so we have some ideas, and we're also going to be here in terms of contributing back as we pick the formats that we're using and where we can help back. We're going to open source and change, commit back what we can.
Sounds great. I think those are all the questions we have. All right. So yeah, I think there were a few questions around whether the slides will be shared. I think we have consensus from everybody that we will upload the slides. You can also head over to the open source website, hudyapache.org. I think we'll upload the slides over there as well. So I'll just take this like a minute to thank all the speakers. Thank you so much for putting these awesome talks together and taking time out from your busy schedules. And also to everybody who attended to take some time out to learn how the Hudi is being used in different companies in different flavors and forms. So thank you, and stay tuned for the next meetup.
Thank you.